Eastern Hungary, October 23, 1944. Staff officers of the 503rd Heavy Panzer Battalion compiled their after-action report in the village of Debrecen. The typewriter clacked through carbon paper, recording numbers that would have seemed impossible weeks earlier. 250 kilometers covered in coordinated operations, 120 Soviet anti-tank guns destroyed, 19 field artillery pieces were eliminated. The Russian Sixth Army was forced to abandon positions around the city. The Tiger II had proven itself, the report concluded, both in armor protection and mechanical reliability. Within 4 months, 45 Tiger IIs of this same battalion would be lost. 10 would fall to enemy action. The remaining 35 would be destroyed by their own crews after mechanical breakdowns or fuel exhaustion left them immobilized. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The most powerful tank fielded by any nation in World War II was defeated not primarily by Allied guns, but by the mathematics of its own design. 68 tons of armor and firepower, rendered immobile by components engineered for vehicles 20 tons lighter. Final drives fractured after 100 kilometers. Transmissions seized under operational stress. Fuel tanks emptied faster than supply columns could refill them. The pattern repeated across every front where the Tiger II fought. Schwerheerespanzerabteilung 501 arrived at the Eastern Front in May 1944 with 45 new Tiger IIs. Technical inspection after rail unloading revealed 8 operational vehicles. 37 suffered final drive failures before firing a shot. The Panzer Lehr Division received 5 Tiger IIs in June 1944. All 5 broke down before engaging Allied forces in Normandy. Crews destroyed them with thermite grenades to prevent capture. In Italy, Heavy Panzer Battalion 504 lost 87 Tiger IIs. 13 fell in combat. 74 were destroyed by their own crews during retreats through mountainous terrain. The Tiger II represented the apex of German armor development and the nadir of strategic judgment. It mounted the most powerful tank gun of the war, capable of destroying any Allied or Soviet tank at ranges exceeding 2,000 meters. Its frontal armor, up to 185 millimeters thick and sloped at 50 degrees, proved effectively impenetrable to every anti-tank weapon the Allies deployed. In direct tank versus tank combat, its kill ratios reached 11-1. Yet for every Tiger II that dominated a battlefield engagement, 2 sat immobilized behind friendly lines awaiting repairs that would never come, or burned beside roads where crews had abandoned them during withdrawals. The question was not whether German engineers could build the world's most formidable tank. They clearly could. The question was whether Germany possessed the industrial capacity, logistical infrastructure, and fuel supplies to field such a vehicle in meaningful numbers. The answer, written in the ruins of 492 Tiger IIs scattered across Europe, was no. Berlin. January 1943. Wehrmacht ordnance offices evaluated intelligence reports from the Eastern Front with mounting concern. Soviet tank production exceeded 1,034s per month. New heavy tank designs appeared in captured documents and battlefield wreckage analysis. The KV-85 mounted an 85mm gun capable of penetrating the Tiger I's side armor at combat ranges. Development continued on heavier variants, including what would become the IS-2 heavy tank with its 122mm gun. Soviet industry. Transplanted east of the Urals beyond Luftwaffe bomber range, operated at full capacity despite the German invasion. American factories shipped thousands of Sherman tanks across the Atlantic under Lend-Lease agreements. The quantitative disparity widened monthly. Germany needed qualitative superiority to maintain any hope of stemming Allied advances. German armaments philosophy had always emphasized superior technology over mass production. The Tiger I, operational since late 1942, embodied this thinking. It weighed 56 tons and mounted the formidable 88mm Kwamok 36L56 gun. This weapon could destroy any Allied tank at ranges exceeding 1,000 meters. Tiger I crews achieved kill ratios averaging 5-1 and sometimes exceeding 10-1 in favorable conditions. But production never exceeded 135 tanks per month. Total Tiger I production would reach only 1,347 vehicles before the line shut down in August 1944. Allied factories produced tens of thousands of tanks during the same period. Adolf Hitler demanded specifications for a new heavy tank that would guarantee German technical dominance, regardless of numerical inferiority. The requirements read like engineering fantasy, constrained only loosely by physical reality. Weight class: 70 tons. Main armament: the new 88mm L-71 gun, with penetration capability against any foreseeable enemy armor, at ranges exceeding 2,000 meters. Frontal protection: impervious to all known anti-tank weapons at combat ranges. Armor geometry: sloped following the Panther's principles to maximize effective thickness while minimizing weight. Speed: sufficient for tactical maneuver and operational deployment. The last requirement would prove impossible to satisfy given the others. Two firms received development contracts in early 1943. Ferdinand Porsche, Hitler's preferred designer who had created the Tiger I's unsuccessful predecessor, proposed an unconventional layout. Electric transmission driven by two gasoline engines. Each engine powered a generator that drove an electric motor connected to one track. Central engine placement. Suspension borrowed from the Ferdinand tank destroyer with 6 road wheels per side on longitudinal torsion bars. The electric drive promised smooth power delivery and excellent low-speed maneuverability. It also weighed over 4,000 kilograms and consumed massive amounts of scarce copper for generators and motors. Porsche was so confident of selection that he began manufacturing turrets before contract award. Henschel und Söhne offered a more orthodox approach, based on conventional mechanical transmission, rear-mounted engine, forward fighting compartment with centrally positioned turret. 9 interleaved road wheels per side on transverse torsion bars, providing excellent weight distribution and ride quality. Mechanical transmission and steering system requiring less exotic materials and proven in previous designs. Both proposals utilized turret designs from Krupp. Both mounted the new 88mm KOK-43 L-71 gun. This weapon represented the pinnacle of German anti-tank gun development. Muzzle velocity of 1,130 meters per second, penetration of 185 millimeters of armor plate at 2,000 meters range. No Allied tank could survive a hit at any practical combat distance. The Sherman's frontal armor, at maximum 51 millimeters, offered no more protection than paper. October 1943. The prototypes underwent evaluation at testing grounds near Berlin. Hitler attended the demonstrations personally. He selected the Henschel design for production, rejecting Porsche's electric transmission as too complex and resource-intensive for mass production. The electric drive also suffered from overheating problems during extended operations. The decision came too late to prevent. Porsche's turret production. The first 50 Tiger IIs would mount these Porsche-designed turrets featuring a rounded front before switching to the improved Henschel turret design with its better ballistic shape and thicker armor. Production authorization came in November 1943, with delivery of the first vehicles scheduled for early 1944. Target: 1,500 vehicles to equip heavy tank battalions across all theaters. The designation: Panzer Kampfwagen VI Tiger Ausführung B, Ordnance Inventory Number SDKFZ 182. German crews called it Königstiger, literally Bengal tiger, but translated as King Tiger. Allied soldiers who encountered it called it the Royal Tiger or King Tiger. Intelligence officers who examined captured examples would call it Germany's most expensive strategic miscalculation. Kassel, Germany. Henschel Assembly Facility, December 1943. The first production Tiger II emerged from the assembly hall. Weight specifications had grown during development as engineers added armor thickness and strengthened components. Combat-loaded weight settled at 69.7 tons. Some estimates placed fully loaded weight above 70 tons when accounting for full fuel load ammunition, crew, and personal equipment. The armor protection exceeded all previous German designs and surpassed every Allied tank by substantial margins. Frontal hull armor measured 150 mm thick, set at 50 degrees from vertical. This slope doubled effective thickness against perpendicular strikes to approximately 300 mm. The lower hull plate stood 100 mm thick at a vertical angle. Turret front, 185 mm. Turret sides and rear, 80 mm. Hull sides, 80 mm. Hull rear, 80 mm. The sloped geometry maximized protection while minimizing weight compared to vertical armor of equivalent effectiveness. British testing after the war calculated that their 17-pounder gun, using armor-piercing, discarding sabot ammunition, could theoretically penetrate the Tiger II's turret front and lower hull at ranges of 1,000, 100 and 1,200 yards, respectively, under ideal 90-degree impact angles. Such perfect angles rarely occurred in combat, where tanks maneuvered and fought at varying orientations. Throughout the war, no verified frontal penetration of a Tiger II turret occurred in actual combat conditions. Allied tank crews learned quickly that frontal engagement meant certain death. Flanking maneuvers became mandatory tactical doctrine. The gun justified every ton of armor protection. The 88mm KOK 43L71 dominated every battlefield engagement where it could be brought to bear. Effective range against enemy armor exceeded 2,500 meters. At this distance, the Tiger II could destroy any Allied or Soviet tank while remaining immune to return fire. Sherman tanks mounting 75mm guns needed to close within 500 meters for any chance of side penetration. Soviet 34 85mm guns and IS-2 122mm guns faced similar range limitations against the Tiger II's frontal aspect. Crews who fought in Tiger IIs reported a psychological advantage approaching invincibility when properly positioned in hull-down defensive positions. The enemy could not hurt you. You could destroy them at will. The mathematics of armor thickness and gun penetration favored the Tiger II absolutely in direct fire engagements, but the powertrain undermined every tactical advantage the armor and gun provided. The Maybach HL-230 P-30 engine sat in the rear hull compartment, 12 cylinders arranged in a 60-degree V configuration, 23.1 liters total displacement, maximum output, 700 horsepower, at 3,000 revolutions per minute. This was the identical engine that powered the Panther medium tank. The same engine was originally designed and developed for 30-ton weight class vehicles during early war development programs. The Panther, weighing 45 tons in combat trim, already strained this power plant's capabilities. Maybach had increased displacement from the earlier HL-210's 21.4 liters to extract more power, but the basic architecture remained unchanged. The Tiger II weighed 68 to 70 tons, depending on combat loading. The engine that struggled to move 45 tons adequately now faced 55% more mass. Engineers calculated power-to-weight ratios during development and testing, 10 horsepower per ton for the Tiger II. Compare this to the Panther, 15.5 horsepower per ton. Sherman M4, 12.8 horsepower per ton. Soviet 34, 18.6 horsepower per ton. The Tiger II possessed the worst power-to-weight ratio of any major battle tank deployed in World War II. This single number predicted the mobility and reliability problems that would plague the design throughout its service life. Test reports flagged the inadequacy clearly. Engineers recommended either lightening the design significantly or developing a more powerful engine. Neither option proved feasible within Hitler's requirements and Germany's deteriorating industrial situation. Production proceeded with full knowledge that the Tiger II was underpowered. The transmission compounded the engine's limitations through complexity that exceeded German industry's ability to manufacture reliably under wartime conditions. Maybach Olvar OG 401216 Model B. 8 forward gears ranging from very low speed for obstacle crossing to highway cruising speed. 4 reverse gears for tactical withdrawal. The pre-selector mechanism allows drivers to choose the next gear before engaging the clutch. Hydraulic control system for smooth shifting. This represented sophisticated engineering at the cutting edge of automotive technology. The system had been developed for lighter vehicles, where its complexity could be justified by improved performance. In the Tiger II, it transferred 700 horsepower through components designed for vehicles weighing 45 tons or less to drive a 68-ton tank through mud, snow, and broken terrain. The steering mechanism used a Henschel L801 unit with double radius design. This allowed the Tiger II to pivot in place by driving one track forward while reversing the other, a capability that proved valuable in defensive positions where the tank needed to engage targets across a wide arc without repositioning the hull. But the double radius design proved vulnerable to shock loads transmitted through the drivetrain during rapid direction changes or when operating on uneven ground. Fork levers fractured under stress. Hydraulic seals leaked. The system required constant maintenance that field conditions rarely permitted. The final drives posed the most critical structural weakness. These reduction gear assemblies, mounted in the front hull, transferred power from the transmission to the drive sprockets that engaged the tracks. They reduced the transmission's output shaft rotation speed while multiplying torque for track propulsion. The Tiger II's final drives had been designed for the Tiger I, which weighed 56 tons. They now supported an additional 12 to 14 tons, while operating under identical or greater stress conditions. Every component in the final drive assembly operated beyond its design parameters. Gears sized for lower loads carried higher loads. Bearings rated for specific weights now bore greater weights. Heat generation increased. Lubrication systems adequate for lighter loads failed to provide sufficient cooling and protection under increased stress. Every kilometre driven multiplied wear beyond engineering tolerances, calculated during the design phase. Fuel consumption revealed strategic impossibility disguised as technical specification. 730 litres per 100 kilometres on paved roads under ideal conditions. Over 1,000 litres per 100 kilometres during cross-country operations through mud, sand, or snow. The Tiger II carried 860 litres total capacity, distributed among 7 fuel tanks located throughout the hull. Theoretical operational range: 120 kilometers maximum during cross-country operations. 170 kilometers on roads under ideal conditions with no combat maneuvering or extended idling. These figures assumed properly maintained engines operating on specification fuel. Germany produced synthetic fuel through Fischer-Tropsch coal gasification plants. This complex industrial process converted coal into liquid fuels through chemical synthesis. The resulting gasoline possessed lower octane ratings than natural petroleum-derived fuel. Lower octane caused pre-ignition in high-compression engines designed for better fuel. Pre-ignition led to detonation, the uncontrolled explosive combustion that damaged pistons, piston rings, and cylinder heads. Carbon deposits accumulated faster with synthetic fuel due to incomplete combustion. Oil contamination increased. Filters clogged more frequently, requiring more frequent maintenance intervals. Engines designed to operate 700 kilometers between major overhauls now required rebuilds after 400 to 500 kilometers when running on synthetic fuel. The Tiger II required the high-quality fuel Germany could not provide to move the distances Germany could not afford. Eastern Front, May 1944. Rail flat cars carried the first 45 Tiger IIs of Schwere Heerespanzerabteilung 501 eastward toward forward positions in Ukraine. Each tank represented 300,000 man-hours of labor from raw materials to completed vehicles. Each cost 321,500 Reichsmarks. Each embodied Germany's commitment to technical superiority over the mass production philosophy that governed Allied industrial strategy. The battalion's organization followed standard structure for heavy tank battalions. 3 companies of 14 tanks, each plus a battalion headquarters section with 3 command tanks. Total: 45 Tiger IIs, representing over 14.5 million Reichsmarks investment and over 13 million man-hours of German industrial capacity. Crews had received minimal training on the new vehicles. Most had transitioned directly from Panzer IVs or older Tiger IS, with only days of familiarization instruction on the Tiger II. The complexity of the pre-selector transmission alone required weeks of practice to master. The massive weight changed every aspect of driving technique compared to lighter tanks. Fuel consumption demanded constant monitoring to prevent running dry during operations. The interleaved road wheel suspension, though providing excellent weight distribution, required extensive maintenance and could jam completely if mud froze between wheels. None of these skills could be adequately taught in compressed training schedules, driven by desperate personnel shortages at the front. The rail journey from Kassel to Ukraine consumed weeks as Allied air superiority forced trains onto secondary routes and necessitated overnight movement to avoid fighter-bomber attacks. Crews performed maintenance during stops at rail stations and sidings. They ran engines to practice turret traverse, which used a hydraulically powered system driven by the main engine. Running engines consumed fuel. Moving parts accumulated operating hours. Wear degraded components before the tanks ever reached combat zones. When the battalion finally arrived at its forward, the railhead, and began the unloading process, technical officers conducted standard operational inspections before releasing vehicles to company commanders. The inspection reports documented catastrophe. 8 tanks passed inspection and were rated fully operational. 37 vehicles suffered final drive failures ranging from minor gear damage to complete housing fractures, not from enemy action, not from combat stress or tactical maneuvering under fire, from the simple act of unloading from rail flat cars and driving short distances of 5 to 15 kilometers to battalion assembly areas. Over 80% of the battalion's strength was immobilized before firing a single shot in anger. Investigation teams examined the failures to determine root causes. Multiple contributing factors emerged. Crews had installed narrow transport tracks for rail movement, as required by regulations. These reduced the vehicle's overall width to fit within rail loading gauge limits, which restricted maximum width for safe passage through tunnels and past platforms. Upon arrival at forward areas, regulations required crews to switch to wider combat tracks immediately. This changeover involved removing transport tracks, installing wider combat tracks, and adjusting track tension to proper specifications. Inexperienced crews, unfamiliar with the Tiger II's specific requirements, frequently tensioned tracks improperly. Too tight placed constant stress on final drives even when stationary. Too loose allowed tracks to ride up and off drive sprockets during turns. The drive sprocket design itself contributed to failures. Original Tiger II design used 18-tooth sprockets, where every tooth engaged with track links during rotation. Production simplification changed this to 9-tooth sprockets, designed to work with new double-link tracks. This meant only alternating teeth engaged with the track. Each engaged tooth absorbed double the force compared to the original design. During gear changes and direction changes, sudden torque variations created shock loads that transmitted directly to final drive components. These sudden jerks, multiplied by the vehicle's massive weight and inertia, fractured gear, teeth and cracked housings cast from increasingly poor quality steel as Germany's access to proper alloying elements diminished. Driver training deficiencies multiplied mechanical stress. The pre-selector transmission required specific techniques. Drivers needed to anticipate terrain changes and pre-select appropriate gears before reaching obstacles or grade changes. Improper gear selection for conditions placed excessive loads on drivetrain components. First gear provided maximum torque for obstacle crossing but limited speed to walking pace. Eighth gear allowed maximum road speed but provided minimal torque. Selecting high gears for low-speed maneuvering or hill climbing forced the engine to lug, generating excessive heat while straining transmission and final drive components. Drivers, accustomed to simpler transmissions in Panzer IVs, lacked the experience to recognize warning signs of overstress. Oil temperature gauges climbed into red zones. Unusual noises indicated gear problems. By the time drivers noticed these warnings, Damage was often irreversible. Repair crews opened failed final drive housings and found systematic destruction. Gear teeth sheared cleanly along fracture lines, indicating overload failure rather than fatigue cracking. Bearing races showed deep scoring from metal-to-metal contact after lubrication film breakdown. Drive shafts twisted, their splines deformed beyond dimensional tolerances for proper engagement. Some housings cracked completely, the cast steel unable to contain the forces generated by 70 tons of vehicle mass, suddenly decelerating or changing direction. One technical report noted that removal of a damaged final drive intermediate shaft required cutting through the 80mm diameter steel shaft with cutting torches. The splines had twisted so severely that normal disassembly procedures using mechanical presses failed. Each final drive failure rendered a tank completely immobile. Each immobile tank represented resources Germany could not spare sitting idle, while awaiting repairs that required spare parts Germany could not deliver on any reasonable timeline. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Western Front, June 1944. Panzer Lehr Division, considered one of the Wehrmacht's elite armoured formations with experienced crews and priority access to equipment and supplies, received 5 Tiger IIs as reinforcement before the anticipated Allied breakout from the Normandy beachhead. These crews represented the best the German army could field, veterans of multiple campaigns, experienced tank commanders who understood armour tactics, dedicated maintenance personnel with proper tools and training, high-priority supply status that theoretically ensured rapid delivery of spare parts. All 5 tanks suffered complete mechanical breakdowns before engaging any Allied forces. The failure patterns matched those reported from the Eastern Front. Final drives fractured under operational loads. Transmissions seized when subjected to the heat and stress of tactical maneuvering. Track systems failed when drivers attempted to navigate the bocage terrain of Normandy with its steep banked hedgerows and sunken roads. Crews followed prescribed destruction procedures to prevent the disabled vehicles from falling into Allied hands intact. Thermite grenades placed in engine compartments melted engine blocks into useless slag. Explosive charges detonated inside fighting compartments destroyed gun breech mechanisms and rendered turrets inoperable. Gun tubes were damaged by firing rounds with obstructed barrels. Optics and radio equipment were removed before destruction if time permitted. British intelligence officers photographed the wrecks after Allied forces overran the positions. Technical teams from the Royal Armoured Corps examined the remains carefully. One officer noted specifically in his report that the tanks showed no combat damage whatsoever, no armour penetrations, no shell impact craters on hulls or turrets, no signs of fire from fuel ignition after battle damage. They had defeated themselves through mechanical failure before contributing anything to the German defensive effort. British engineers studied the final drive assemblies and transmission components recovered from wrecks. Their reports noted the fundamental mismatch between component design specifications and vehicle operating weights. The conclusion: German engineering excellence undermined by strategic pressure to field increasingly heavy tanks using inadequate industrial capacity and scarce materials. Normandy, July 18, 1944. The first Tiger IIs entered actual combat during the British Second Army's Operation Atlantic. Heavy Panzer Battalion 503 deployed its first company between the villages of Troon and de Mouville to defend against the offensive aimed at capturing Caen and breaking into open country south of the city. Tiger IIs, positioned in prepared defensive positions with hull-down concealment, performed exactly as designed. The long 88mm gun reached out beyond 2,000 metres. British tank columns advancing across open ground presented perfect targets. Sherman Fireflies mounting 17-pounder guns attempted to engage at maximum range. Their rounds glanced off sloped frontal armour without penetrating. Cromwell cruiser tanks stood no chance at any range. The Tiger IIs destroyed British armour with methodical precision. Crews reported kill ratios exceeding 10-1 during the initial defensive engagement. British commanders quickly learned that frontal attacks against Tiger II positions meant unacceptable casualties. Tactical doctrine shifted to emphasizing flanking maneuvers, artillery suppression, and airstrikes, rather than direct tank combat. But movement revealed the Tiger II's systemic weaknesses that static defensive fighting concealed. Battalion maintenance logs documented specific failures that would repeat across all Tiger II units throughout the remaining war. Final drive intermediate shafts. Splines twisted under torque loads when tanks repositioned between defensive positions. Replacement required disassembly of final drive housing, a minimum 8-hour job requiring specialized lifting equipment. Sprocket teeth. 50% showed heavy wear or complete shearing after 50 to 100 kilometers of operational movement. Track tensioning devices. Spindles broken or threads stripped from housings when crews attempted to adjust tension on worn tracks. Steering mechanism components. Fork levers fractured under shock loads when drivers executed rapid direction changes during tactical withdrawal under fire. The track design itself created ongoing problems that engineering changes could not fully resolve. The simplified double-link configuration meant only 9 of 18 sprocket teeth engaged with tracks during rotation. This uneven engagement pattern created sudden jerks during direction changes when torque suddenly transferred from one set of teeth to another set. These jolts transmitted directly through the drivetrain to final drives not designed to absorb such shock loading. Each direction changes slightly damaged components. Cumulative damage from dozens or hundreds of direction changes during tactical operations caused eventual failure. Engineers recognized the problem clearly. Proposed fixes required complete redesign of track systems and sprockets. Time and resources for such fundamental modifications did not exist. Production continued with known deficiencies. Henschel's chief designer, Erwin Aders, wrote candidly in October 1944 that the failure occurred because the Tiger II went into production without considering test results properly. This extraordinary admission came from Germany's senior tank designer, acknowledging that strategic pressure and production schedules had overridden basic engineering prudence. Test programs had revealed these weaknesses during prototype evaluation. The decision to proceed with production anyway reflected Germany's desperate strategic situation. The need for heavy tanks to counter Allied numerical superiority outweighed considerations of mechanical reliability. Wolfgang Thomale, Inspector General of Panzer Troops responsible for overseeing all German armoured forces, briefed Adolf Hitler personally on November 4, 1944 regarding complaints from field units about Tiger II reliability. Thomale's statement to Hitler addressed the specific complaints that repeatedly appeared in unit reports. These complaints, he explained, could be traced to the new track design adopted to simplify production. Although the double-link track represented considerable manufacturing simplification compared to original single-link designs, it created greater susceptibility to mechanical failure during field operations. The engagement of only alternating sprocket teeth caused sudden jerks in the final drive that the components simply could not withstand under the vehicle's massive weight. Thomale announced that a new track design was under development, but warned that implementation would require months. Units would have to continue operating with known deficiencies. German engineering reports throughout the Tiger II's production run repeatedly used the term Kinderkrankheiten, literally children's diseases, translated as teething problems to describe these failures. The phrase suggested temporary difficulties that would resolve with minor modifications and improved production techniques. This optimism ignored or obscured the fundamental engineering reality. The Tiger II's final drives were designed and rated for vehicles weighing 56 tons. They now supported vehicle weights of 68 to 70 tons. No modification short of complete redesign with larger, stronger components could bridge that 14-ton gap. The transmission was engineered and tested for vehicles weighing 45 tons. It now transferred power to a vehicle weighing 55% more. Heat generation increased proportionally with load. Lubrication systems that adequately cooled and protected components at design weights failed catastrophically under the increased thermal stress of actual operations. Components that might have provided reliable service for 1,000 kilometers in a vehicle matching their design specifications failed at 100 kilometers when installed in the overweight Tiger II. Every operational hour ran components closer to failure thresholds. Every kilometer driven exhausted the limited reserve capacity engineered into the design. The Tiger II did not suffer from teething problems that could be fixed with minor adjustments. It suffered from fundamental design mismatch between vehicle weight and component capabilities that no amount of field modification could resolve. Kassel. Henschel Factory Complex. Production schedules called for aggressive output increases throughout 1944 to provide heavy tank battalions with sufficient vehicles to replace combat and mechanical losses. Initial production rate, 1 vehicle per month in late 1943 during initial tooling and workforce training. Planned target, 145 vehicles per month by mid-1944 once full production tempo was achieved. Reality. Production peaked at 85 units per month during brief periods and never sustained that rate. Average production hovered around 60 to 70 vehicles per month during peak periods. Each Tiger II required 14 days of assembly time, from when the hull entered the final assembly line until the completed vehicle rolled out for acceptance testing. But this figure counted only the final assembly. Total manufacturing time, including component production and sub-assembly work, totaled 300,000 man-hours per vehicle when all supporting work was calculated. For comparison, American factories produced Sherman M4 tanks with approximately 30,000 man-hours per vehicle from raw materials to completed tanks. German Panzer IV production required 60,000 man-hours per vehicle. The Tiger II consumed 5 times the labor of the reliable, proven Panzer IV design. This labor could have produced 5 Panzer IVs for every Tiger II manufactured. Those 5 Panzer IVs would have provided better operational availability, easier maintenance, simpler logistics, and greater battlefield presence than a single Tiger II that spent more time under repair than in combat. Cost analysis made the strategic absurdity even clearer. Each Tiger II cost 321,500 Reichsmarks from materials purchase to delivery. Each Panther cost 117,000 Reichsmarks. Each Panzer IV cost 103,000 Reichsmarks. Each Stooge 3 assault gun cost approximately 54,000 Reichsmarks. For the resources devoted to manufacturing 1 Tiger II, Germany could have produced 2.7 Panthers or 3.1 Panzer IVs or almost 6 Stug 2. All 3 alternatives offered proven reliability in field service, established logistics and supply chains, and significantly greater operational availability rates. The Tiger II's superior armor protection and gun performance meant nothing strategically if the tank could not reach the battlefield, remain operational once there, or be supported with necessary fuel and spare parts. Allied strategic bombing destroyed German production capacity faster than factories could expand or relocate. 5 separate bombing raids between September 22 and October 7, 1944, specifically targeted the Henschel plant at Kassel. 95% of factory floor space was destroyed or rendered unusable by structural damage, fire, or disruption of essential utilities. Production halted completely for several weeks, while crews cleared rubble and attempted to restore basic manufacturing capability. Estimated production loss from these 5 raids alone: 657 Tiger IIs that would never reach frontline units because the factories producing them were reduced to rubble before vehicle completion. By March 1945, monthly production had collapsed to just 25 vehicles as continued bombing, raw material shortages, and labor force disruptions combined to strangle industrial output. Total production through war's end: 492 Tiger IIs. Original orders had specified 1,500 vehicles to fully equip all planned heavy tank battalions. The shortfall of 1,008 tanks represented not merely lost production, but wasted investment in factory tooling, workforce training, and logistics infrastructure designed to support a much larger fleet that never materialized. The numbers manufactured mattered little if completed vehicles could not reach combat zones in operational condition. Rail transport of Tiger IIs required special equipment and careful route planning. Vehicle weight exceeded standard rail flat car load ratings. Railroad engineers calculated that many bridges along potential routes could not support the weight of fully loaded tank trains without risk of structural collapse. Route restrictions forced longer journeys on rail networks already congested with military and industrial traffic. Allied fighter bombers systematically targeted marshalling yards, rail junctions, and key bridges with increasing effectiveness throughout 1944 and into 1945. Tank trains sat immobilized for days or weeks awaiting track repairs, bridge reconstruction, or alternate routing around destroyed infrastructure. Crews performed maintenance during these rail delays to keep vehicles operational. They ran engines periodically to keep batteries charged and to circulate oil through engine components to prevent corrosion from condensation. They practiced turret operation using the hydraulic system powered by the main engine. These necessary activities consumed fuel from vehicles' limited tank capacity. Engine operating hours accumulated before tanks reached combat zones. Normal wear degraded components that had no accumulated mileage, but showed deterioration from running hours under load. A tank that arrived at the front after 2 weeks of interrupted rail travel might have consumed 20 hours of engine operation sitting on flat cars. Those 20 hours represented 3% of the engine's 700-hour service life between major overhauls spent before the tank moved under its own power in tactical operations. Material quality deteriorated steadily throughout 1944 and into 1945 as Allied bombing systematically disrupted supply chains for critical alloying elements. Armor plate specifications called for specific percentages of molybdenum, nickel, and other elements to ensure proper balance of hardness and toughness. Molybdenum prevented brittleness. Nickel improved impact resistance. Strategic bombing cut Germany's access to foreign sources of these materials. Domestic substitutes were employed out of necessity. Vanadium partially replaced molybdenum. Chromium substituted for nickel in some applications. The replacement alloys produced armor that met thickness specifications but lacked proper metallurgical properties. British and Soviet metallurgical analysis teams examined armor plate from captured Tiger IIs and found significant quality problems. The armor showed brittleness, indicating inadequate alloy content. Impact testing revealed a tendency toward catastrophic cracking rather than ductile deformation. In combat, this meant that even large-caliber rounds that failed to penetrate could create dangerous conditions inside the vehicle. When Soviet 122mm or 152mm high-explosive rounds struck Tiger II armor without penetrating, the impact shock caused the brittle armor to crack and spall on the interior surface. Fragments of the tank's own armor became projectiles inside the fighting compartment, causing crew casualties from rounds that technically had not penetrated the armor. Final drive components showed similar quality degradation with even more immediate operational consequences. Design specifications called for nickel-bearing steel, heat-treated to specific Rockwell hardness standards. Heat treatment protocols required precise temperature control and specific quenching rates to achieve proper grain structure in the steel. By 1944, nickel supplies were exhausted by competing demands from U-boat production, aircraft engines, and other high-priority programs. Ersatz alloys using available materials substituted for specification steel. Heat treatment protocols were shortened from hours to minutes to maintain production schedules as factory throughput demands increased. Gears were machined to looser dimensional tolerances when precision machine tools wore out and replacement parts became unavailable. Quality inspection checkpoints were reduced from 12 stations, checking different specifications, to 8 to speed vehicles through final assembly. Each compromise, individually minor, multiplied the probability of premature failure when combined. Each cost-cutting measure, individually justified by production necessity, reduced operational lifespan when effects accumulated. Field units reported final drive failures occurring at 60 to 80 kilometers, when technical manuals promised a minimum 150 kilometers before first scheduled maintenance. Transmissions that should have lasted 500 kilometers between rebuilds failed at 200 kilometers. Engines designed for 700-kilometer service intervals required major overhauls at 400 kilometers when running on low-octane synthetic fuel that accelerated wear through carbon deposits and inadequate lubrication. Spare parts logistics collapsed completely under sustained Allied air superiority over German transportation networks. Central depots stockpiled replacement final drives, transmission assemblies, and engine components awaiting rail transport to field units that never arrived. Field units filed requisitions through proper supply channels for components needed to return disabled tanks to service. Requisitions sat in depot files for months without fulfillment. Rail capacity was prioritized for ammunition and fuel. Spare parts shipments remained in warehouses. When trains were available, Allied fighter bombers attacked anything that moved during daylight. Supply trains travelled only at night on circuitous routes. Journey times tripled or quadrupled. Many trains never reached destinations. Maintenance crews improvised field repairs using whatever materials came to hand. They cannibalized completely disabled vehicles to obtain parts to keep other tanks operational. Cannibalization ratios climbed steadily throughout the war's final year. By early 1945, field reports documented ratios of 3 immobilized tanks stripped to maintain 1 operational vehicle. This meant that of any 4 Tiger IIs in a company, only 1 fought while 3 served as involuntary parts donors, sitting immobile in field workshops. The arithmetic of availability spiraled downward in a self-reinforcing cycle. Fewer operational tanks meant greater pressure to cannibalize disabled vehicles for parts. More cannibalization meant fewer total vehicles that could potentially be returned to service when spare parts eventually arrived. The cycle consumed itself, converting Germany's most expensive tanks into stationary parts depots. Hungary, October through November 1944. The 503rd Heavy Panzer Battalion conducted operations during the Debrecen offensive that would produce the after-action report documenting one of the Tiger II's rare sustained successes. 250 kilometers covered in coordinated movements split between 2 battle groups, operating with different divisions on different days. The extremely tough and steadfast enemy identified in the report as Soviet penal battalions composed of punishment troops fighting under threat of execution was shaken to the core by the energetic assault. German forces threw Soviet communications networks into total confusion through systematic destruction of supply columns and a transport train carrying reinforcements and ammunition. These actions forced the Russian Sixth Army to abandon prepared positions around the Debrecen area and withdraw eastward. The battalion's after-action report praised Tiger II performance in unusually positive terms compared to earlier assessments. The total distance was accomplished essentially without mechanical failure. The tank proved itself extremely well, both in armor protection and mechanical perspective. Vehicles that received up to 20 direct hits without disablement were not uncommon throughout the operation. This single operation became the Tiger II's showcase success, the validation that German propaganda needed to justify the massive resource investment. Individual engagement outcomes from Debrecen justified the design philosophy that prioritized firepower and protection above all other considerations. March 20th, 1945, Eastern Austria. A single Tiger II, commanded by an experienced crew, engaged a Soviet armored spearhead attempting to bypass German defensive positions. The after-action report credited this single tank with destroying 15 Soviet tanks in a single afternoon engagement. SS Hauptsturmführer Bernstein's Tiger II destroyed 17 enemy tanks the following day in a similar engagement, supported by 2 Panther tanks providing flank security. These exceptional performances demonstrated what the Tiger II could accomplish when mechanical systems functioned properly, when adequate fuel was available, when experienced crews operated the vehicle, and when tactical situations allowed the tank to fight from prepared positions, exploiting its strengths while minimizing exposure to its weaknesses. But operational availability determined strategic impact far more than tactical lethality in individual engagements. The same 503rd Heavy Panzer Battalion that achieved success at Debrecen provides the clearest statistical evidence of the Tiger II's fundamental problem. Between January and April 1945, operating on the Eastern Front, this battalion claimed approximately 500 enemy vehicle kills, tank destroyers, assault guns, and tanks of all types included in this total. The kill ratio appeared impressive: 500 enemy vehicles destroyed, 45 Tiger IIs lost. 11 points 1-1. But analysis of how those 45 Tiger IIs were lost reveals the truth. 10 vehicles were destroyed by enemy action in combat. 35 were abandoned and destroyed by their own crews after mechanical breakdowns or fuel exhaustion left them immobilized far from recovery assets. 78% of losses resulted from non-combat causes. Only 22% fell to enemy fire. The most powerful tank in the world was defeated primarily by its own design, rather than by Allied weapons. This pattern repeated across every unit that operated Tiger IIs in every theatre. Battle of the Bulge, December 1944 through January 1945. 52 Tiger IIs committed to the Ardennes offensive. 1st SS Panzer Division deployed 45 Tiger IIs. The 12th SS Panzer Division fielded additional vehicles. Kampfgruppe Paper, the spearhead formation tasked with achieving the deepest penetration toward the Meuse River, advanced with Tiger II support as its heaviest armour. Initial attacks on December 16th achieved tactical success. American defensive positions crumbled, infantry units fell back in disorder, but the advance quickly outran German fuel supplies. Kampfgruppe Piper captured several American fuel dumps intact but found them stocked with gasoline rather than diesel. German tanks used gasoline engines, but the captured American fuel was the wrong octane rating. Tiger II engines suffered detonation and pre-ignition when running on American fuel formulated for trucks rather than high-performance tank engines. By January 8, 1945, operational status showed 15 Tiger IIs remained mobile and combat-ready. 11 sat immobile awaiting repairs. The remaining vehicles had been destroyed by crews during withdrawal or abandoned when fuel exhaustion made recovery impossible. Allied fighter bombers destroyed supply columns attempting to reach forward units. Fuel trucks burned on frozen roads. The most meticulously planned German offensive since 1940 fell apart, partially because the heaviest tanks could not be sustained logistically. American forces who recaptured ground lost during the initial German assault photographed dozens of abandoned Tiger IIs. Intelligence reports noted that most showed no combat damage. Crews had destroyed them during withdrawal using standard procedures. Thermite grenades melted engines. Explosive charges shattered transmissions. The tanks defeated themselves. Normandy, August 1944. German forces withdrew toward the Seine River, attempting to escape Allied encirclement forming around Falaise. Tiger IIs from multiple battalions littered retreat routes. British technical intelligence teams photographed intact vehicles sitting beside roads. Canadian engineers examined wrecks to determine failure causes. American ordnance officers supervised removal of selected vehicles for shipment to testing facilities. Intelligence reports compiled from these examinations reached consistent conclusions. Most Tiger IIs showed no combat damage indicating destruction by enemy fire, no armor penetrations, no impact craters from high explosive rounds, no fire damage from ammunition detonation after battle hits. The vehicles had been deliberately destroyed by their own crews using standard demolition procedures before abandoning positions during withdrawal. Crew destruction protocol followed established patterns. If time permitted, crews removed gun breech blocks, radio equipment, and optical instruments for evacuation with the crew. Thermite grenades were placed in the engine compartment directly on the engine block. Detonation melted aluminum components and warped steel beyond repair. Explosive charges went into the fighting compartment to damage gun mechanisms and render the turret inoperable. If insufficient time existed for thorough destruction, crews fired rounds with obstructed barrels to split the gun tube or used explosives to blow off tracks. Minimum destruction rendered the vehicle immobile, and the main gun unusable. These procedures ensured that even captured vehicles provided minimal intelligence value to Allied technical teams and no operational value if Allies attempted to use them against German forces. The pattern of systematic destruction indicated that crews understood their vehicles were too heavy to tow efficiently and too valuable to leave operational for enemy capture. Recovery of disabled Tiger IIs required specialized heavy equipment. Only other Tiger IIs or the massive Berger Panther recovery vehicle possessed sufficient power to tow a 68-ton dead weight. Berger Panthers existed in insufficient numbers. Using operational Tiger IIs to tow disabled ones doubled fuel consumption for the towing vehicle while exposing both tanks to enemy fire during slow movement. Field commanders made rational decisions to destroy disabled vehicles rather than sacrifice operational tanks and scarce fuel in recovery attempts with low probability of success. Italy. Schwerpanzerabteilung 504, 87 Tiger IIs lost between initial deployment and final surrender. Combat action accounted for 13 losses from direct enemy fire, mine strikes, or artillery hits that disabled vehicles beyond field repair. The remaining 74 were destroyed by crews during withdrawals through Italian mountains. The mountainous terrain of Italy multiplied mechanical stress on Tiger II drivetrains beyond tolerances that might have been adequate on flat terrain. Steep uphill grades forced drivers to select low gears, placing maximum torque loads on transmissions and final drives. Engine cooling systems, barely adequate for level ground operations, proved insufficient during extended climbs. Temperatures soared beyond safe operating limits. Engines overheated, coolant boiled. Cylinder head gaskets failed from thermal stress. Descending steep grades required constant braking, using the transmission to limit speed. This practice, necessary to prevent runaway acceleration on descents, generated tremendous heat in transmissions never designed for such duty cycles. Narrow mountain roads provided no space to bypass disabled vehicles. A single Tiger II blocking a mountain pass trapped entire columns behind it. Recovery attempts in mountains required specialized equipment unavailable to field units. Cranes capable of lifting final drive assemblies for replacement could not be transported up mountain roads. Field workshops existed only in valley towns far from forward positions. Disabled tanks could not be towed down narrow switchback roads, carved into mountainsides. Tactical necessity forced immediate decisions. Either destroy the disabled vehicle to clear the road for following units, or abandon the entire column trapped behind one broken tank. Commanders made the only rational choice available. 30 of the 74 non-combat losses occurred during April 1945, as the battalion withdrew northward during final Allied offensives. Each loss represented 300,000 man-hours of German labor. Each represented 321,000 Reichsmarks of scarce resources. Each represented Germany's dwindling industrial capacity squandered on vehicles that could not be sustained in field operations. Statistics compiled on March 15, 1945, revealed final operational readiness across all German armoured forces. These figures came from reports filed by every division and independent battalion. Tiger II. 59% operational readiness. Panzer IV. 62% operational readiness. Panther. 48% operational readiness. The Tiger II, Germany's newest and theoretically most advanced tank, achieved lower operational availability than the older, simpler Panzer IV design dating from the late 1930s. Complexity defeats reliability. Sophistication ensured breakdown. Advanced technology proved meaningless without the industrial capacity and logistics infrastructure to support it. The 59% figure represented optimal conditions, with units in rear areas conducting maintenance with adequate parts and fuel. Operational readiness during active combat operations dropped to approximately 40%. During retreats, when units moved frequently and maintenance time was limited, readiness fell below 20%. These percentages meant that of every 5 Tiger IIs assigned to a battalion, only 1 participated in combat, while 4 sat immobile awaiting repairs. Soviet technical testing of captured Tiger IIs provided the most damning assessment of the design's fundamental problems. Captured vehicles underwent controlled testing at Kubinka Proving Ground outside Moscow. Soviet engineers conducted systematic evaluation programs to assess German tank capabilities and inform future Soviet designs. 20 Tiger IIs were driven on test courses until mechanical failure ended each trial. Average distance to complete immobilization, 138 kilometers. Longest operational run achieved, 270 kilometers before catastrophic failure. Shortest run, 46 kilometers before complete breakdown. Every vehicle failed mechanically before exhausting ammunition or fuel supplies. Every failure traced to drivetrain components unable to cope with vehicle weight under operational stress. Soviet conclusions appeared in technical bulletins distributed to Red Army units. The Tiger B's weakest components are its final drives, drive wheels, and track pins. This assessment matched reports from German field units, from British technical teams examining captured vehicles in France, and from American ordnance officers testing Tiger IIs shipped to Aberdeen Proving Ground in Maryland. American testing confirmed Soviet findings through independent evaluation. A captured Tiger II underwent standardized U.S. Army trials, designed to assess reliability, maintainability, and combat effectiveness. The vehicle completed basic mobility tests, measuring acceleration, top speed, and turning radius. These tests required limited mileage and could be accomplished despite drivetrain weaknesses. Endurance testing revealed catastrophic inadequacy. The transmission seized completely after 89 kilometers of road driving and tactical maneuvering. The engine required major overhaul after 430 kilometers, when cylinder compression testing showed excessive wear and oil consumption exceeded acceptable limits. American test conclusions stated plainly, unsuitable for sustained operations under American doctrine. U.S. Army doctrine emphasized operational mobility, rapid repositioning, and sustained offensive operations covering hundreds of kilometers. The Tiger II's mechanical fragility made such operations impossible. American analysts emphasized that their doctrine valued reliability over maximum performance. A tank that could fight today, tomorrow, and next week held more value than a tank with superior gun and armor that spent most of its time deadlined awaiting repairs. British technical teams reached similar conclusions after examining Tiger IIs captured in northwest Europe. Detailed reports analyzing final drive failures noted that components exhibited tooth shear patterns consistent with shock overload and insufficient lubrication. Metallurgical analysis showed heat-affected zones, indicating repeated thermal cycling beyond design limits. These scientific assessments confirmed what German field reports had stated repeatedly. The Tiger II's drivetrain could not sustain the loads imposed by the vehicle's excessive weight during tactical operations. French forces examined the vehicle abandoned near Mantes-la-Jolie, discovered after the crew had destroyed the engine and transmission before withdrawing. The tank sat beside the road with tracks still intact and turret still traversable manually. Engine problems had forced abandonment. When French engineers inspected the transmission after cutting through destroyed components, they found fractured gears identical to failures documented in German, British, and Soviet reports. The Tiger II influenced post-war tank development primarily through negative examples. Allied designers studied captured vehicles to identify features worth incorporating into future designs and weaknesses to avoid repeating. Western tank development adopted sloped armor geometry that maximized protection while minimizing weight. The British Centurion employed well-sloped frontal armor, providing excellent protection within acceptable weight limits. High-velocity guns became standard for post-war main battle tanks. American, British, and Soviet designs all incorporated long-barreled high-velocity weapons capable of long-range engagement. But Allied designers universally rejected the Tiger II's complex drivetrain architecture, its underpowered engine relative to weight, and its problematic interleaved road wheel suspension. The British Centurion design emphasized reliability alongside firepower. The Rolls-Royce Meteor engine, developed from the famous Merlin aircraft engine, provided adequate power with proven durability. The Merritt-Brown transmission offered simplicity and reliability rather than complex pre-selector mechanisms. American M26 Pershing development prioritized proven drivetrain components over maximum performance. The Ford GAA engine was a known quantity with established manufacturing and proven field reliability. Soviet T-54 design incorporated the Tiger II's armor slope principles, while retaining the mechanical simplicity that had made the 34 successful. The T-54 used conventional transmission and suspension designs that Soviet industry could manufacture reliably and that field units could maintain without specialized equipment or extensive training. All three post-war designs reflected lessons learned from analyzing Tiger II failures as much as from studying its successes. The consensus emerged that armor protection and firepower were important but insufficient. Operational reliability, ease of maintenance, and sustainable logistics determined whether a tank design succeeded strategically regardless of its tactical capabilities. A tank that could fight effectively 1 day per week due to constant mechanical problems provided less value than a tank with inferior armor and gun that remained operational 6 days per week. Availability outweighed capability. Sustainability exceeded performance. These lessons shaped tank development for decades afterward. Germany. Synthetic fuel production statistics revealed strategic impossibility underlying Tiger II operations. Peak German synthetic fuel production, 5.5 million tons annually achieved in 1944 before Allied bombing reduced output. This figure represented total production of all fuel types for all military and essential civilian uses. The Luftwaffe consumed massive quantities for aircraft operations. Kriegsmarine required fuel for remaining surface vessels and U-boats. Wehrmacht ground forces competed for allocations. The civilian economy needed minimum fuel supplies to maintain food distribution and essential industries. Available fuel had to be distributed among all these competing demands, while production fell throughout the war's final year. Tiger II fuel consumption, 730 litres per 100 kilometres. A single tank moving 200 kilometres consumed 1,460 litres. A company of 14 Tiger IIs moving 200 kilometres consumed 20,440 litres. 20 metric tons of fuel for one company, making one operational movement of moderate distance. For comparison, a German infantry division required approximately 40 tons of supplies daily, including fuel, ammunition, food, medical supplies, and all other necessities. One Tiger II company moving tactically consumed half an infantry division's daily fuel allocation. A battalion of 45 Tiger IIs conducting a 200-kilometre march consumed 65,700 litres, 65 metric tons of fuel for one movement by one battalion. Mathematics became unsustainable quickly. Germany produced thousands of armoured vehicles competing for fuel supplies. Panzer divisions required fuel for Panthers, Panzer IVs, half-tracks, trucks, and reconnaissance vehicles. Panzer Grenadier divisions needed fuel for their mechanized infantry carriers. Artillery, battalions consumed fuel, moving their guns. Supply trucks required fuel to deliver ammunition and supplies to frontline units. Every military vehicle competed for allocations from shrinking production. Tiger II units received priority status theoretically, guaranteeing adequate fuel supplies. Reality rarely matched theory. Allied strategic bombing systematically targeted synthetic fuel plants throughout 1944 and 1945. Each raid reduced monthly production. By late 1944, fuel production had fallen 70% from peak output. Less fuel available meant tighter rationing across all units. Soviet offensives in the east and Allied advances in the west forced constant German repositioning. Mobile defense doctrine required rapid movement to counter enemy breakthroughs. Counterattacks demanded quick concentration of armor at threatened points. Tiger II units received movement orders and fuel allocations insufficient to execute them. Battalions began movements with partial fuel loads. Tanks ran dry en route to assembly areas. They sat abandoned beside roads while crews marched forward to infantry positions. Germany's elite heavy tank battalions transformed into stranded monuments to logistics failure. The fuel required to move one Tiger II 200 kilometers could have moved two Panzer IVs 400 kilometers. Better allocation of scarce fuel resources might have provided greater operational impact, but German doctrine fixated on qualitative superiority through advanced technology rather than quantitative adequacy through mass production of simpler systems. Poland. January 1945. Soviet Vistula-Oder offensive shattered German defensive lines. 6.7 million Soviet personnel, 33,000 artillery pieces, 7,000 tanks. 4th Panzer Army defending the frontage collapsed within 72 hours under assault of overwhelming force. Tiger II units received retreat orders as Soviet spearheads penetrated deep into rear areas. Temperature, -25 degrees Celsius. Lubricants in Tiger II drivetrains thickened to the consistency of tar. Oil viscosity increased dramatically in extreme cold. Gear oil that flowed freely at normal temperatures became semi-solid. Engines required preheating before starting attempts. Crews used blowtorches to heat oil pans. Some units lit fires beneath engine compartments. Both methods were dangerous, inefficient, and time-consuming. Cold starts, even after preheating, damaged engine bearings catastrophically. Metal components contracted at different rates during extreme cold. Critical clearances designed for normal operating temperatures tightened when temperatures dropped 50 degrees below normal. Pistons seized in cylinders. Connecting rod bearings froze to crankshaft journals. Oil pumps could not circulate oil thick as grease through passages designed for free-flowing liquid. First engine revolutions after cold starts scored bearing surfaces before adequate lubrication reached critical components. Even engines that started successfully often failed within kilometers, as thermal stress from uneven expansion cracked castings and warped cylinder heads. Cooling systems designed for moderate European climates froze solid. Water coolant expanded as it froze, cracking radiator cores and cylinder blocks. Coolant lines burst. Engines that remained mechanically sound became inoperable without functional cooling systems. Panzer Regiment 5. 72 Tiger IIIs, on unit strength according to morning reports. 27 mobile phones after cold weather immobilized the remainder. Crews worked frantically to restore disabled vehicles. They drained frozen coolant and refilled with alcohol mixtures that resisted freezing. They heated engines for hours before attempting to start. Recovery efforts became futile as Soviet advance units approached from multiple directions. Remaining operational Tiger IIs withdrew westward. Immobilized vehicles were abandoned after crews destroyed them. Soviet forces captured approximately 150 serviceable Tiger IIs during January and February 1945 as German forces retreated across Poland. Soviet technical evaluation teams examined captured vehicles. Their reports confirmed conclusions from earlier testing. Engines showed minimal combat damage. Most vehicles suffered transmission failures, final drive breakdowns, or fuel exhaustion rather than battle damage. The 501st Heavy SS Panzer Battalion withdrew toward Austria during final Soviet offensives. The battalion conducted night movements to avoid Allied aircraft that dominated daylight skies. Several Tiger IIs broke down during darkness. Others ran out of fuel when supply trucks failed to reach forward positions. No recovery vehicles accompanied the column. Battalion standing orders required immediate destruction of any vehicle that could not maintain movement. Crews executed destruction procedures they had practiced dozens of times throughout the retreat: thermite grenades, explosive charges, breech block removal. Each loss was irreplaceable. Production had effectively ceased. No replacement vehicles existed. Every Tiger II destroyed represented one less available for defense of Reich territory. The same week that saw multiple Tigers abandoned to mechanical failure also witnessed successful engagements that demonstrated vehicle capabilities when mechanical systems functioned. March 20th through 22nd, German forces established temporary defensive positions blocking Soviet spearheads. Tiger IIs destroyed 32 Soviet tanks in 3 days of fighting. Favorable terrain allowed German crews to engage from prepared positions at long range. Superior optics and guns dominated the battlefield. But successful tactical engagements could not overcome operational collapse. Defensive victories meant nothing when the line could not hold. Orders came to withdraw again. More Tiger IIs broke down during movement. More were abandoned. More were destroyed by their own crews. The cycle repeated until few remained. France, August 1944. Falaise Pocket encirclement. Approximately 50,000 German personnel captured, 500 tanks lost. Tiger IIIs represented approximately 1/3 of total tank losses. Fewer than 10% showed primary combat damage when British and Canadian forces examined them. Remainder displayed evidence of mechanical failure, fuel exhaustion, or deliberate destruction. Intelligence officers photographed serial numbers on hulls and turrets. Technical teams measured armor thickness and documented construction details. Engineers disassembled transmissions and final drives on site to understand German engineering approaches. Every examination revealed the same pattern: outstanding weapon when functioning, inadequate reliability under field conditions, drivetrain components unable to sustain operational loads, design fundamentally compromised by weight exceeding component capabilities. Technical Intelligence Report conclusions stated, outstanding weapon compromised by inadequate mechanical reliability. The assessment acknowledged Tiger II strengths clearly. Gun performance was exceptional, armor protection unmatched, crew visibility and fire control were excellent, while documenting fatal weaknesses with equal clarity. Drivetrain fragility limited operational employment. The maintenance burden exceeded field capability. Fuel consumption rendered sustained operations impossible. Complexity exceeded available infrastructure and training. The recommendation to Allied tank designers: study the gun and armor. Reject the drivetrain and logistics requirements. Do not attempt to replicate the German approach of maximizing individual vehicle capability while ignoring operational sustainability. Belgium. September 1944. Abandoned Tiger IIs lined retreat routes from the French border to the German frontier. Allied intelligence officers systematically photographed each vehicle. Serial number documentation allowed tracking of production batches and identification of manufacturing facilities. Each captured vehicle provided intelligence about Germany's declining material quality through metallurgical analysis. Armor samples showed inferior alloy content. Transmission components displayed inadequate heat treatment. Statistical analysis of all captured and destroyed Tiger IIs revealed brutal mathematics. Total Tiger II production, 492 vehicles. Peak simultaneous operational deployment, approximately 200 field-ready tanks at any single moment. Operational readiness averaged 60% under optimal conditions. Under combat stress, 40%. During retreats, 20%. Of total losses across all fronts, approximately 55 to 60% resulted from mechanical breakdown and abandonment, 25 to 30% from direct combat, 15 to 20% from fuel-related desertion when recovery proved impossible. Germany. September 1945. The United States Technical Mission examined captured vehicles systematically after hostilities ended. Engineers measured wear patterns on gear teeth. Metallurgists analyzed armor plate composition and heat treatment. Mechanics disassembled complete drivetrains, component by component. Findings confirmed every battlefield report. Mean transmission life, 100 to 150 kilometers under operational conditions. Mean final drive service life, similar duration before catastrophic failure. Operational readiness during combat operations, 40% maximum, The Tiger II that looked invincible on paper proved fragile in practice. The design that promised to restore German qualitative superiority instead consumed resources better allocated elsewhere. Aberdeen Proving, Ground, Maryland. Captured Tiger II No. 303 underwent complete evaluation according to U.S. Army testing protocols. Mobility trials measured acceleration, top speed, cross-country performance, and obstacle crossing. The vehicle performed adequately in these limited-duration tests. Endurance testing revealed fundamental inadequacy. Transmission locked up after 89 kilometers of mixed road and cross-country operation. Clutch worn beyond service limits. Gears showed excessive wear. Final drives exhibited early failure indicators. The engine required major overhaul after 430 kilometers. Compression testing showed cylinder wear. Oil consumption exceeded specifications. Piston rings are no longer sealed properly. American conclusion: unsuitable for sustained operations under U.S. doctrine emphasizing operational mobility and strategic flexibility. Soviet post-war analysis reached identical conclusions through independent testing. The Kubinka facility tested 20 captured Tiger IIs until mechanical failure ended each trial. Average operational distance, 138 kilometers. Patterns held across vehicles from different production batches, different factories, and different time periods. Early production vehicles from 1944, late production vehicles from 1945, all failed mechanically within similar distances. All demonstrated identical weaknesses in identical components. Final drives inadequate. Transmission overstressed. Engine underpowered for vehicle weight. The design flaw was systematic, not random quality variation that could be addressed through improved manufacturing. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.